Good morning, everyone. You don't know how happy I am to see you, particularly some of you in the last minute. I will give just a few words before starting the program of this morning. Basically, for those that you are not being involved in the project in the beginning, what is SHui projects? In this project, there are 19 European, Israeli, and Chinese organizations, including 2 small companies. One is here with Aviva. Those are all the institutions involved in SHui. And we have been working since August 2018 on these 3 major lines. First, we started building a data set of long-term experiment plus expertise and interaction with stakeholders. We made a strong effort of analyzing with different kinds of crop and hydrological models ways to optimize the use of water, and we try to integrate that, developing policy recommendations, but also practical tools like some of one will be talked today. This is the delegation of the regional government of Andalusia in Brussels. They have been extremely helpful, and not also helpful, quite warm. We have been really protected by them, trying to set up this. Also to the people of the SHui delegation that we try. You realized this morning that it wasn't there, so we had to move it for technical reasons. I want to thank particularly to the participants in the roundtable. You are going to give 2 or 3 days of your work or your holidays to be here, and we already enjoyed yesterday evening with you. And to our project officer, Adelma Di Biasio, who has tried to do the best to bring some policy officers to the roundtable that unfortunately, believe it or not, broke her wrist yesterday. So that will be one of the changes. Well, that will be all from me as an introduction. This is southern China, a tropical area with also a lot of erosion issues that we work with in the project. Well, thanks for being here and our best wishes for the day. And now, Juan José Alarcón will be, instead of Diego Intrigliolo, they work together and they will be so calm to give the first talk on optimizing, on using deficit irrigation.
Well, the communication was presented, eventually presented by Diego Intrigliolo, that the most of you know very well, but finally he has some personal problems, and I will do it. Our idea is to talk about the actual potential of deficit irrigation, sensors, and differentiated species management to optimize water use under droughts. Well, the total index is one. Before in the beginning, we will do some. Yeah, it's not because they're online or something like that. Because I think that the people listen to me, but anyway. The first is we will talk about the context of this kind of studies. We will talk also about deficit irrigation, sensors, and precision irrigation. Well, the context is that we have a serious problem of water scarcity in the world, basically by the climate change. And it's true that in the world there is a lot of water. It's about 1,400,000 million cubic kilometers. But you can see here is only 2% fresh water. So this fresh water, obviously, is not all of them available for us. And finally, we have only a very small amount of water for water resource to use by us, by humanity. And besides of this, the most of this water is used today by the irrigation. About the 70% of the total water resources that are available for us are used in the world in irrigation. So, well, we have a problem. The irrigation consumes a lot of water, and we have a serious problem of water scarcity in the world. So it's necessary, obviously, to manage properly the water resource in the agriculture. In order to manage the water resource, we can work in the sources of water, superficial and groundwater resources. We can use water transfer to transfer the water from one place to other place. Obviously, are very important the reservoirs and also some special strategies like wastewater reuse, etc. And we can work also in the demands. We can improve our irrigation system by the irrigation engineering, irrigation agronomy, irrigation physiology, etc. Until 19th, the water management activity were mainly related to increase the source availability. But from 2000, the pillar for agriculture water management is more based on the demand management. What is this, how is possible to manage, to improve this demand management? I think that there are two different approaches. One is the governance, that is very important, and sure that during the day we will talk about that. But also the use of water use efficiency tools technology. Water use efficiency tool technology, and this is the topic that I will talk today. There are different approaches when we consider water use efficiency. The physiologists normally consider the water use efficiency like a transpiration efficiency, and they estimate this transpiration efficiency like the ratio between photosynthesis and stomatal conductance. Obviously, they are more interested into obtain efficient organisms, new varieties, new genotypes that are more efficient in the use of water. The agronomists are more interested in the water productivity, that is the ratio between yield and evapotranspired water, and they are more working in the improvements of the environments and the development of different management practices to improve the water use efficiency. Well, who is more important, the approach, the physiologists or the biotechnology or the agronomists strategies? Here you can see one. Well, it's difficult to. No, well, you can see here what is the situation. If you don't use any an improvement in the irrigation systems, baseline, you can see that you consume a lot of water to obtain a very small production. If you only apply biotechnology strategies, that is to improve some genotypes and to use some species that are more tolerant to the water stress and something like that, you can see that for the same amount of water, you obtain more yield. If you only apply irrigation technology, you can see that with less water, you can obtain more production. And finally, the best one is this, to join the biotechnology and the irrigation strategies in order to improve the water use efficiency in the plants, in the crops. One strategy to improve the water use efficiency is the application of regular deficit irrigation. That you can see here, the strategy, the principle of the regular deficit irrigation is that the plant sensitivity, that the plant don't need to cover all the water necessity during all the phenological period. There are some times that it's not necessary to cover all the water necessity, but it's not important for the final production, for the total yield of the plant. And well, in SHui and also in other projects, but in SHui, some of us, we are working in different strategies, different regular deficit irrigation, different genotypes, different species, etc., in order to know how this strategy, this tool is working for different species. As I told you, the regular deficit irrigation, it's a little difficult, is based on create water deficit during specific phenological events to save water while minimizing negative impact on yield. And with this, we can have two different objectives. The first is to save water, obviously, in situations of water scarcity, but also it's important that this kind of water stress, that controlled water stress that we are doing, is also good to improve the quality of the crops. And you know that today for the agriculture, for the farmers, it's not only important the quantity of the yield obtaining, also the quality of the crops or the fruits that we obtain. Well, this is some examples that when we apply regular deficit relation strategies, this is some different studies, and you can see that when you apply this kind of strategies, a small reduction or some reduction in the application of water. Here you have relative applied water, like about 60%, only produce some reduction in relative yield of 20%. So this is a strategy that is working very good. This is some examples that we also obtain in citrus, in kaki, pomegranate, local grapevine. Here is that we can compare the total water applied in irrigation, in control, in regular deficit relation strategies. You can see that this regular deficit relation strategy is normally supposed to save water about 15%, between 15 and 20%, sometimes a little more, but the average is about 15 and 20% of save water. Obviously, this reduction of water and maintaining the production improves in all the cases the water use efficiency. In some cases, you can see that this increase in the water use efficiency in regular deficit irrigation could be about 43 or 30%. Normally, it's about 20 also. And the other important thing that I told you before is not only important to save water, it's also important to improve the fruit quality. You can see that if you study the total solids in citrus, kaki, promenade, in all the case, in almost all the case, the fruits that are obtained in regular deficit irrigation have more quality than in the control plants. Well, it's not very easy to apply regular deficit irrigation. It's more easy to talk about that than to apply, because there are different aspects that obviously are working in this. It's necessary to study very good the soil, the culture condition, climatic, irrigation system, obviously the drought tolerance, the specific period of growth of the different plants, and finally you can establish this kind of elaboration of the regular deficit irrigation strategies for each crop. To apply this regular deficit irrigation, it's necessary, as I told you before, to study, to know very well the situation of the plant, but also the water in the soil and also the climate condition. And for this, it's very important to work with, with sensors. The most of you, you know that there are a lot of sensors now in the market, no? A lot of some in the soil, some in the plant. We are working, especially with this kind of sensor. That is this feather reproof that you can see that it's possible to measure the water volume or the humidity in the soil at different depths in the soil, and of course this is an automatic system that you can see exactly what is the level of humidity that are in the soil for when you apply irrigation or apply the irrigation, etc. Here is an example of the application of this kind of probes. Here you can see this is the different irrigations that we are applying, and you can see in each event of irrigation, obviously we observe one increase in the water humidity in the soil. When you stop the irrigation, like here, you can see that the water humidity in the soil is down, and it's down to zero, basically. And later, when you irrigate again, you can see that again, you can see one increase of the water humidity. So, well, this kind of data are included in algorithms and all these things, and finally, we can use this kind of sensor to improve the irrigation management. Problems of this kind of soil probes. Well, the main problem is that the soil is very heterogeneous, and well, this is a local sensor that is included in one specific point. So you have this orchard. Obviously, the sensor also only is in this place. So it's not sure if this is a good representative of all the orchard. Even in the same tree like this, well, the study is doing in one specific point in the soil. Well, normally is working very good, but sometimes maybe there is some variation in the root distribution or something like that. And finally, these measurements that you are doing are not the same, are not the better one. Another approach to another kind of sensors, another approach to study very well the water status in the plant, obviously is to use the plant to know exactly what is the situation, to measure plant water status using sensors in the plant. There are a lot of sensors in the plant. Maybe the most useful, the most interesting one, and maybe the more efficient one is the stem water potential, but it's not time to talk about them. But the stem water potential is difficult to, it's not an automatic sensor, it's not an automatic measurement. So we need to find some sensors that can work in an automatic way. As I told you, there are different sensors. I'm sure that most of you know very well some of them. Like the sat flow, you measure the sat flow in the trunk of the plant. Obviously, some control of temperature detection in the canopy, in the leaves. There are also leaf turbo sensor applied in the leaves, and also there are some sensors to measure trunk growth determination, and these measurements are very, very related with the level of water stress or the status, the water status that has a plant. Well, in SHui, we are working also in this kind of sensors. We test different kind of sensors. We try to improve them. We can, it depends on the different genotypes or different species. We must test who of these sensors are better. It's not time to talk very much about all of these sensors, but maybe, especially in Murcia, we are working very much, we are working very much in this trunk diameter fluctuation. In the trunk diameter fluctuation, you can see that here there is like a needle that is close is in union with the trunk. And here this is a displacement transducer. So the movement of this needle inside of this transducer obviously is recorded by the data logger, and these micro changes in the trunk during the day are recorded during the day. And this is very relevant because this is something like that. You know, this is the needle, and you can see that this is the evolution that you obtain during the day. In the night, the trunk is expansive, and during the day, with the evapotranspiration, the trunk suffers some small reduction in the diameter that we are watching in this kind of system. This is relevant because this micro difference, this micro change in the trunk are very different if the plant is well irrigated or if the plant is stressed. Here you can see, wow. Here you can see what happened with the plant has a very good irrigation. You can see that the difference between the measure that you have in the night, you have in the midday, are less that when the plant is very, very stressed. Why? Because when the plant or the tree is very stressed, obviously they need to use the water that they have in the special trunk. If there are water enough in the soil, normally they use this water, and it's not necessary that the reduction in the trunk is so high. So again, as I told you before, in SHui we are working too much in this. In the same way that the soil sensors, obviously all the data must be integrated in some algorithms and all these things in order to manage the irrigation. In any case, this kind of sensor, local sensor, we have the same problem that with the soil. Independent of there are plant or water, we determine the water status in a single spot within a plot. And this is something that we can avoid using remote sensing techniques. These remote sensing techniques that are using different sensors that are translated by plane or by drone or something like that, permit to observe the water status not only in one specific point in the orchard. You can see the water status in the general, in the total orchard, in all the area, in the all irrigation area. This is something like that. This is the measurements that you have in one orchard or vineyard. And you can see that there is a very important variability in this area that is not especially big, but there is important difference in the level of water that are in the soil, in the cover of vegetation, etc. So with this kind of remote sensing, we can see this difference, and we can use this, for instance, to optimize the irrigation system design. If you see that there are some places that the plant needs more water, obviously you must improve, you must increase the amount of water that you must put in this area, and to reduce in the area that the plant maybe needs more for different reasons. So this is the irrigation precision. And another possible use is that is also done in SHui by some of Bruce that maybe will be exposed later, is the selection of the optimum sensor location. So sometimes we told before that when you apply some plant sensor, soil sensor, it's difficult to know in what plate you must put because the variability could be very high. So the first thing that you can do is to use this remote sensing in order to know the variability that they have in the orchard, and after this you can select in what specific place you must put the sensor. So to finish my talk, in this kind of activity, we obtain results, and the results, wow, what happened here? The results is improvement of water use efficiency in different countries in pilot site using the regular deficit irrigation strategies. Also in SHui we have improved the local sensors, plant and soil, some different kind of sensors in order to know better the plant water status and to optimize the water use efficiency. And finally, also we are working too much in the improvement of remote sensing in order to optimize the irrigation system design. All of this with the general objective of to save irrigation water in a context of water scarcity induced mainly by the climate change. So that's all. Thank you very much.
Okay. Thanks so much, Juan Jose. Since we have a really tight schedule, the plan is to have these short presentations and then we can catch up in the coffee break with Juan Jose, okay? So thanks again. And now the floor is to Thomas Dostal from the Czech Technical University at Prague.
Thank you. Thank you. I should present here. Well, actually, previous presentation was about irrigation. And we are hydrologists. I'm representing a group of people from Czech Technical University in Prague. We are, let's say, hydrologists. and soil scientists, and we were working in less dry areas. If we can do something not to irrigate, because what was presented before was if we irrigate, then how to irrigate and how to measure it and so on. But in some cases, we don't really have to irrigate, and if we can do something about it. So aim of our activity within the project was to assess potential of various measures, what we can do, how to do it, how to influence, let's say, small water cycle, how to store more water in a landscape. Then try to quantify these effects, then to test effectiveness of measures and strategies also for soil erosion control measures as a soil conservation, and then to elaborate catalog of best management practices, which is one of important outcomes of the project issued as Jose Gomez and team last year, where those strategies are described in a linkage to European Union policy. What I'm going to talk here about is mainly soil conservation tillage, soil conservation agriculture, and its effect on small water cycle. We understand it as one of, let's say, soft strategies to reduce water scarcity and to avoid technically relatively complicated irrigation measures. What we considered were conservation tillage, which we understand as only topsoil, shallow soil is disturbed and not plowed, not turned up. Then no-till technologies, and then mulching, so crop residues. We worked in both directions, so field experiments and also modeling. Field experiments, we used a field rainfall simulator, pretty big one, 8 by 2 meters, on typical Wischmeyer slopes, 9% slope steepness, with a rainfall intensity 60 millimeters per hour, which is pretty high, we know, but on the other hand, the problem which are for the water in the moderate areas like Central Europe are those rainfall events, heavy rainstorms, because if you have heavy rainstorms, then the excess of water which is not stored in a landscape is flowing out. It causes to us flash floods, as we faced last week, let's say in Czech Republic, in Central Europe. And we lose this water in landscape from total annual amount. So this is what we are talking about, this part of water. Then our simulation was always 30 minutes, so-called dry run. So we are raining on the dry soil. And then after 15 minutes, next 30 minutes on a wet run. So we simulate how a landscape behaves when it's fully saturated by the water and rainfall comes. What is exactly what happened in Central Europe last week, where one storm by other was coming day by day, and we are really facing, people were really suffering a lot. Yes. From field experiments, what we can see here, I'm not going to go to details to the charts, but if we take a fallow, then you see how the surface runoff and soil erosion occurs, and then this is the wet run, dry conditions, and then surface runoff and also soil erosion starts with some delay. Here delay is just about 5 to 7 minutes, but we are talking about fresh fallow which was compacted, so seedbed conditions. We have 5 to 7 minutes to start. Here at the wet conditions, it starts immediately. And then it gets balanced. So this is the stage when a landscape is fully saturated and the landscape is not able to catch any water anymore. So with care for the landscape, we are influencing this part. This is what we are affecting. We can affect here in dry conditions what will be delay, how long the soil is able to store the water before surface runoff starts, and then when it starts, how steep it is. Potentially with the wet conditions as well, if we are able to store some water or not. Okay, there are just some experiments, some examples on the mice. We tested 4 different types of crops growing: conventional, contour farming, shallow tillage, and direct seeding. You can see how those technologies of conservation tillage are able to improve soil quality, I mean retention capacity. So there is significant reduction of surface runoff, reduction to 83, which is here, between conventional and shallow tillage, up to 17 for the main growing season. Well, those 3 stages, there are growing seasons, like initial stage, full vegetation, and ripened vegetation. What is interesting is that the ripened vegetation is in fact more risky than seedbed conditions, because here soil crust is well developed and vegetation is only, it's nearly dry. Then we stepped over to mathematical modeling. We did much more simulations, of course, but we went to mathematical modeling to assess effects of various scenarios of control measures and strategies, to go to various scales from plot to farm to catchment, to test different models. Typical way is to calibrate models, to validate them, and then to model scenarios. And then we had testing data sets from catchments in Czech Republic, in Austria, in Spain, in Israel, and in China. Well, in plot scale modeling, we went to detailed modeling in 1D by very advanced physical-based model, Hydros 1D, for which we use for quantitative assessment of the effect of best management practices on those 6 test areas which I mentioned, 2 in China, 1 in Israel, 1 in Czech, 1 in Austria, and 1 in Spain. And the effect, again, we tested no tillage, conservation tillage, and mulch residues. We indicated positive effects of mulching as the best seemed to be for, to store most of the water. Important for us was that it was valid for all the areas, regardless of climatic region, field crops, country, or soil type. And because we are simulating only in 1D vertical flow, so lateral flows and parcel sizes and boundary effects were not considered. But you see the effect is in single percent, in units, in single percent. So we can say that's not much. But assuming that the soil, topsoil, is the biggest retention volume, retention space in a landscape, then each single percent, it's a lot of water. Then we move to bigger scale, to SWOT. SWOT is Soil and Water Assessment Tool, probably the most widespread model around the world. Modeling hydrology, soil erosion, sediment transport, also nutrient transport. It describes a landscape distributed to so-called hydrological response units, which are understood to be homogeneous based on soil type, slope, land use. And it was calibrated and validated at several catchments from about 0.5 square kilometers to 100 square kilometers in Czech Republic and Austria. What we found out in Czech and also Austria, average annual reduction by contour tillage, no tillage, and no tillage with cover crops. Thank you. So reductions are pretty high, I would say even very high, and I will come in the very end to those numbers to interpret them. We found it's easy to use, it's well representing. For the farm scale, we modeled also not only agricultural conservation practices, but also landscape structure changes. In the management scale, it also confirmed big effect up to 30 times reduction. Soil conservation practices have showed much bigger effect on surface runoff reduction than changes in land use scenarios, which was a little bit surprise, but as I said, topsoil is the biggest retention space in a landscape, bigger than water reservoirs. Then if we come to reality, how is it with conservation agricultural practices in Europe according to Eurostat values? Conventional tillage is green, conservation tillage is blue, and zero tillage is a red. So this is ordered by magnitude by the extent of conservation tillage. And I was searching if the countries with a water scarcity, with a potential water scarcity, have significantly more application of soil of conservation tillage practices. But you see Malta, Croatia, Italy, nearly none. Greece, some, Spain, some, Portugal. It's very advanced. So there is no correlation between application of conservation tillage practices and soil and water scarcity. And this is something what's really very urgent, because this is a change in application of conservation practices. Up to 2016, there were no better data, but within last 6 years, and you see that number of countries, there is not full list, there are half of countries are missing, I don't know why, but there are a lot of countries which just go back to conventional, who are giving up conservation tillage and they are returning back to conventional tillage. If I come to results, then everyone would ask for quantification. So tell me how much, what is the effectiveness? Give us a percentage. And my answer is, this is very difficult. In TV, we always hear the percentage and the values, but quantification is extremely difficult. Proportional retention is function of rainfall amount, rainfall intensity, initial conditions, soil properties, general and also actual, and actual crop development stage. So you hardly can say that you store 50% of total water, because if your rain is 10 millimeters over whole day, then you store 100%. If your rain is 100 millimeters during 1 hour, then you are very happy if you store 10%. So then the percentage, what I can mention, overall, it can be stated between 20 to 90% for soil erosion reduction, and between 5 to 80% in water retention, in runoff control. You hardly can say something more precise. And very last, conservation agricultural, it's definitely a way to increase landscape water storage, water availability for crops. Water which we store in a landscape is then available for the crops. That's easy, that's very simple mathematics. It supports soil structure, hydraulic conductivity, resistance, surface roughness, reduces surface runoff up to 90%, has enormous potential of soil erosion control, supports also biodiversity and soil biota, and farmers shall be stimulated to apply, because we could see that trend is definitely not just one way or positive. And this is all from myself. Typical many repeated pictures from our Austrian colleagues showing this is conventional and no tillage, which shows perfectly well the effect. On the other hand, it's a perfectly well taken picture for certain amount of rainfall. If the rainfall would be more intensive, then whole the field would look like that. But for some proportion of landscape of the rainfall, you perfectly can see very wet surface here and water starts to run over here while nothing here. Thank you very much.
Okay, thanks so much, Thomas. And now to give, and thanks to the two speakers for the timing, has been pretty good. And now we are giving the floor to our friend Gianni Quaranta from University of Basilicata. Fantastic.
Hello. Do we have a presentation? Okay, thank you. So, I'd like to share with you this morning in a very rapid way some work we have done in the last months, let's say. So, the idea is to have a cost-benefit analysis in order to understand which are the possibility to change alternative or to assess alternative agricultural practices with three main crops in Europe and one in China. And of course we have done this work based on the data that are available. In particular, in Europe, we forced somehow to use statistical data. At least we have lots of statistical data, but they are the official one, the one that you provided, because unfortunately, we have no access to direct information at farm level. At least we cannot have specific data at farm level. While this was possible actually in China, they worked on their main crop, that was rice, and their analysis was a more, let's say, standard cost-benefit analysis that was based on farm data, farm direct collected data in China. We tried to do what we could actually, according to the data that were available, trying to understand which kind of economic performance were possible for the European farms, and also through trying to understand the environmental performance, so trying to link them. And we also actually, according to the work of our colleague Ioannis Spanos in Greece, we also made this analysis using a carbon and water footprint. Was the approach? As I mentioned, we made use of different statistical techniques using the network of farm accounting available in Europe. Actually, I have to say that we used the 2019 data that were the last one available. It was a huge set of data. But now, I mean, we should, if we had postponed the analysis 3 weeks ago, the European Commission announced a new network of data collection that is about including a lot of sustainability indicators that would be very useful, but unfortunately we could not count on them in our analysis. So we made use of different statistics technique for in order to find, I will show you some results later on, trying to find the sustainability among different factors and of production, but also the sustainability among environmental factors and economic factors in order to improve, to give more efficiency to the system. For the carbon and footprint analysis, it was based on, let's say, standard technique, very, I mean, known technique with algorithm made, calculated on, I mean, current literature, the leading literature. What was the model we used? We have computed 31 indicators. Indicators were calculated based on the data available, of course, at EU level, and we grouped these indicators in 5 classes, 5 dimensions. These were sustainability indicators set, or at least, I mean, we grouped all these indicators in a way that put together all the sustainability indicators, then also indicators from the economic, so about the economic results, also farm assets and structure of cost, and also subsidy and any kind of incentives to produce that we have in Europe for the production. Actually, in this analysis was also corroborated with a sample, well, not a really representative sample, but just to have some, you know, at least to increase our confidence in the results that we get. So we also distributed a questionnaire in both in Spain, in Greece, and in Italy. The same questionnaire actually was used also for at the same time collecting also information for carbon and water footprint. I mean, what is the analysis that we performed? We performed the analysis, as I said, in Europe with these 3 crops. There was olive, grape, wine, cereals. As I said, there was a rise in China. We are here going to present some results just for olives because also for time constraints. But I mean, the results just to show the approach and some findings for the olives, while we I mean, remind for the deliverables that are almost ready for 5.6 and 5.8 for the SHui, I mean, deliverables that we are preparing at the moment. So, what is the first one is how to have the cost structure analysis or some of the results. Not surprisingly, actually, but it's good to when we go inside these, that could be a trivial analysis, saying that look, according to the input, the cost of input, there is a general decreasing. We move from the classes, from the economic classes, growing. I mean, we have a slight reduction in the cost. this means, is really nothing very new on that, although it's not true for all the inputs. And why I'm stressing this aspect? Because we are looking for substitutability. I mean, if we can, inside this, with this approach, we try to find if it's possible, in order to have the same economic results, to substitute some inputs, some maybe environmental friendly inputs with, we can substitute them with some others input, for example, labor or innovation techniques or so on. The first thing that we, the first very basic result was that this was almost true for all the regions that we analyzed, and we find that this, slight, there is a kind of, according to the farm sites, how we move from the, this is just a show, it's not nothing, no numbers here, no figures here, just to see the trend. So the input, the cost input are decreasing, slightly decreasing with farm sites. This is, as I said, could seem a result quite trivial, obviously, because we can experience some economy of scale, as we say. But if we go deeply in this analysis and find to see the behavior of different indicators, we find some, not surprise, but at least I think it's very interesting from the economic point of view. As I said, we based the analysis only on olives. The first surprise, let's say, was that was, strongly statistically supported, so very, that, for example, for the fertilizer, we both, the share of cost of fertilizer according to the farm sites is increasing. As we move from small farms to bigger farms, the cost, the share of fertilizer cost increase first, and then increase also the amount of, not only the cost, because maybe the cost could be even linked to some other stuff, although strange for the sites, but also it's interesting that also the amount of fertilizer is increasing with farm sites. And this was observed, all over the regions that we, at least according to the statistical data. While, for example, other crops, other costs were, slightly decreasing. Of course, the general results, including also the water, was a general reduction. But here, for example, we can observe that the other inputs, machinery, energy, even though the energy was, just at the border of the statistical significance, but at least for the other, so the other input cost, they were reducing according to, as we move from smaller to bigger farm. So in this case, and if we put all these together and saying, okay, this let's take in mind, these results when we move to a multivariate analysis, trying to find relationship among different inputs, and this, what we can observe in this case is that everything is actually linked to the water, because the water, the input, the support or the given by the water is completely different. So in the olive sector, what we can observe for sure is that the different inputs have a different behavior, according to the farm size or even for the physical size of the farms, and but the water is moving in a different way. In economic terms, we should, in strictly economic terms, we observed, that that we as production function regarding the olive trees. The production function of the olive grow in Europe have already used all the potential that we can gain from the fertilizer and also from the crop protection, machinery, and energy. We are in a way that the marginal productivity of these inputs are almost decreasing. Means that we already explored all the potential of this input. I mean, we used this input in order to increase the production, and we, according to, I mean, the set of fertilizer and crop protection, we almost used, the maximum that you can use. In other words, in order to reach, for example, better results or better, higher production from these using more fertilizer, for example, we should use always more and more fertilizer in order to have the same amount of increasing in output. While this is not true for the water. So the water is the only input, actually, that can still, we can, if we use an extra liter of water, we get a better result than the previous liter one. I'm not sure that if I was clear, but just saying that the water marginal productivity is still increasing in olive cultivation in Europe, while the other inputs, fertilizer, and have already reached the, let's say, not maximum, but the highest marginal productivity that we can get. So to have more product, let's say, to increase the production of olive, we need to, we can use a little bit more water rather than fertilizer. So, this is the results, let's say, or in strict economic terms. From where we observe these results? This comes from the kind of sustainability analysis. The question was, can we substitute some of the inputs among them in order to build, for example, management practices that can be more adaptable, more sustainable in some way? The answer is, is yes, if we can account on water, where we can have some sustainability. And unfortunately, the answer will be no, if we cannot have access on water resources, even for the olive production in southern Europe. At the end, just to mention another analysis that we, too fast, just, sorry. Okay, no. So, okay, we just, no, it was, no, one. Okay, no, just to the last, I would like to mention something in the end of another model that we applied for olive was the PCI in order to understand the possible environmental gains using some, trying to observe, according to the data we analyzed, to see when olive grow is together with some other crops, which are the possible, let's say, environmental gains. And actually, we observed, according to the PCI, the principal component analysis, that when olive was in the same farm mixed, for example, with the livestock or with agritourism, we can reach much better environmental results even this was also true, I mean, all over the Mediterranean side. So there is a part of oliviculture in southern Europe that are trying to gain environmental, I mean, results, trying to mix oliviculture with some other crops or even activities in the farm, because it seems that is the only way that we can reach these results. Moving to the okay, this was just some picture of the plots that we used. We can okay, already stress these. My heart now goes to Ioannis, who is no, just a few slides. No, two slides. My heart goes to Ioannis, who is suffering in one of the island bay at the moment. So he sent us these 2 slides about suffering under the sun. I mean, he's not suffering at all on the beach. No, I'm joking, of course. So he performed this carbon and water footprint analysis. He actually sent last night, sent me some notes on it because he was expected to intervene today, but unfortunately he could. Anyway, I mean, the message I think he would like to share, to send us, was that the analysis he performed was based on different, in case of the water, different kind of water for the footprint, and in reality this was quite trivial for the green water, because most of the olives, especially in Italy and Greece, they are rain-fed, while most of the irrigated oliviculture stay in Spain. But these are the results that I'm sure that you can find much better comments in the liver, but he is going to prepare. At the end, the last slide from Ioannis was, I mean, the main message was that olive is still very important for the carbon footprint, because it accumulates more carbon that is going to meet in the environment. So, and these can be even improved according to different techniques like pruning, or if we use, I mean, all the technique that we can still, there are some possible, I mean, strategies to improve or to reduce, I mean, the carbon footprint of the olive grove. I'm sorry, but I know many other comments from this part of the slide. So, thank you.
Thanks so much, Gianni, because you have taken a difficult part of the project in the last months, not only today, you and Rosanna. So now I'm very happy to see that you are here and also that you are healthy, Gabriel. And well, I'm pretty sure you're going to give a pretty nice presentation right now.
Thank you, Jose. So, good morning, everyone. First, I'd like to acknowledge the people who really did the work behind these slides. It's Shannon de Roos and Louise, they are present here, and Michael Bechtold. So these are the 3 core people. And then we have other people who helped, Dirk Kraas, who is also present here, then Zenko Hevaert, Jonas Mortelmans, Samuel Scherer, and Maxime van den Bossen. So it's a whole team, because you'll see we achieved a big step. Several regions in Europe are currently thirsting for water. There's too little water in the soil, and consequently, they're suffering a reduction of biomass. I think I need a pointer. Here you go. Yeah. Yeah, great, thanks. So think of the south, think of the Po Valley regions in Spain, which are currently having an agricultural drought. So that's why we want to look into regional applications. We will monitor these processes via regional modeling, but also via satellite data. And ideally, we want to combine both the models and the satellite data via data assimilation. Okay, pointer, here we go, data assimilation. So, a little bit closer, okay, thanks. So that's going to be the first part of my talk, talking about regional modeling and satellite data, and then we will look into the future, see what our irrigation needs will be under different climate scenarios. So to start with the regional modeling, we use AquaCrop, which is a field-based model, but we extended it so that it now can be run at a regional continental scale. In that process, we converted it from Pascal, the source code Pascal, to Fortran and made it ready for open source distribution. I'll come back to that later. That regional system has been tested with several different meteorological forcings over Europe. Reanalysis data from MERA2. It's a NASA-based product. Also reanalysis data from EasyMap, which has multiple different models behind it. And in addition to that, also climate forecasts. So reanalysis is looking back in history. Forecast is looking forward. We evaluated the regional system in terms of soil moisture and biomass, and then having assured ourselves that everything works well, we could then predict future irrigation requirements. So AquaCrop version 7 will hopefully be launched at the end of this month if FAO approves. What we currently have available is a version-controlled Fortran code available on GitHub. The link is there. If you would click on it, you cannot access it yet because it's still password protected until it'll be approved. Related to that, there are 3 types of applications which will be available to all of you. 3 standalones for 3 operating systems, so Windows, Mac, and Linux systems. Then there is the default graphical user interface, which allows you to manually play with AquaCrop and run simulations at a single field or point. And then the big upshot here is that we implemented AquaCrop inside NASA's land information system, which also allows you to assimilate satellite data, run uncertainty estimates, estimate parameters, do a whole variety of applications. So we'll look a little bit into our first results with these regional systems. Here you see one growing season of AquaCrop simulations of biomass. On the right hand of each pair of panels, you see AquaCrop simulations. On the left-hand side, you see satellite estimates of biomass. So it's the Copernicus dry matter productivity product. You see that biomass is growing. We are in July or August, and then it's declining by the time we get into October. It's nice to look at these maps. Now we compute some performance metrics from taking those pairs of data, and then we compute a correlation, anomaly correlation, an unbiased RMSD, a bias, and this is a total available water storage. This is a soil texture information in essence. You see that the correlation is really high. That's, of course, because of the seasonal pattern. Here you see an example at the Howell catchment with simulations and observations nicely following the same seasonal pattern. So correlations are high. Anomaly correlations regionally are high. In other regions, they're lower, for example, because texture may be off or we didn't simulate irrigation. But still, anomaly correlations tell us something about the interannual variability. So one year you may have more biomass than another. And so in general, it's good. Then other metrics, I'll leave you to look at it. Just to tell you that we looked into different metrics to evaluate biomass. This is at the 1 kilometer resolution. We also used in situ data of soil moisture and satellite data of soil moisture. Here is an evaluation of a regional simulation over Europe at a 50 kilometer resolution using EasyMap input data as forcing, and it's evaluated against SMAP soil moisture retrieval. SMAP is a microwave mission that gives us soil moisture estimates. Here the unbiased RMSD is computed, and it's around the uncertainty of the satellite data. So that's telling us that this model is performing reasonably well, both in terms of soil moisture and biomass and with different types of forcing data. You already see some gaps here. That's because satellite data are not always everywhere available. And that brings me to the second part. We also have satellite observations. So in the previous slides, we used the satellite data to evaluate our model. Now, the model we know is uncertain. On the other hand, we have satellite data, which also give us regional data. They are also uncertain. Currently, there are about 4,000 active satellites orbiting our Earth, of which about 1,000 can be used for Earth observation. And I've circled a few here that observe either soil moisture or vegetation via microwave signals or optical signals. And what we use right now is Sentinel-1 because it has a fine resolution, 1 kilometer, and it detects both vegetation and soil moisture together with an active sensor. We will now use the satellite observations together with the model because we assume and we expect from literature, of course, that the combination of both models and observations would give us the best estimate of soil moisture and biomass. So how does this work? So we start at a specific time in the beginning here, and we let aquacrop run forwards. And you see different lines, that's for the uncertainty. The model has some uncertainty. Whenever the satellite has an overpass, so when data become available, we stop for a second, we assimilate, we ingest that satellite data, we correct our model, we restart it, and then let it predict forward until we get to the next time step. When there's a new satellite product available, we compare both the observation and the simulation, we weight both based on their uncertainty, and we just let the model further evolve. That's the idea of data assimilation. You see also that at each time step, when the satellite is available, the uncertainty reduces. So now let's look at how that looks like at one single time step. So at each single time step, we produce maps of all the different variables, soil moisture in different layers. This is a top layer, this is a deeper layer of aquacrop, and also biomass. This is one snapshot in time. Associated with each of these variables, there is also an uncertainty estimate. Here is an example of the uncertainty on the biomass at this particular day. Now let's look into a time series. This is at the Howell catchment. The top plot is again soil moisture. The bottom plot is biomass. The red line is a model only, without any data assimilation, so no satellite data involved. The red line is where we do assimilate Sentinel-1 data, so microwave data. I'll spare you the details, but we're really assimilating microwave signals, so we need to translate that microwave signal to soil moisture and biomass. And so that's what's happening here. For example, the red line is the open loop. The data assimilation pulls the biomass towards the right value. So this year, that means the biomass is higher than the model predicted. The next year, biomass is actually lower than the model predicted. On top of that, you see that the uncertainty, so going from the red plume to the black plume, the uncertainty decreases, which means that at each time step, we have the lowest possible uncertainty in the data assimilation system. See, these are all nice features. Let's again look at one snapshot in time, now over northwestern Spain. Top row is again soil moisture, bottom row is biomass. It's really a zoom into a particular region. So this is a soil moisture at the beginning of April. The satellite passes over, and you see that it observes the left-hand side of this area. That means over that area, we update our soil moisture and we can update our biomass. And associated with that is a reduction in uncertainty. So we have a reduced uncertainty in our soil moisture estimate, and we can thus make better decisions. On the right-hand side, you see the increments. So that's how much water was added or subtracted from soil moisture by Sentinel-1 at this time step. So most of the time, water was added here. In terms of biomass, there was also a little increment. You see a little change in uncertainty, because of course in the beginning of April at this location, there was very little biomass, probably very little uncertainty and little room for improvement. That is how the data assimilation works. Again, we reduce our uncertainty, we have better estimates, so normally we should be able to make better decisions on water use. And also foresee where we will have yield reductions or loss of yield. That's for monitoring agricultural processes right now. If we look into the future, we get climate change, and maybe we can run our system to then estimate net irrigation requirement. We all know that CO2 emissions may keep rising in the future. There's many different scenarios possible depending on the politics, right, and decisions that people make. We can have an unmitigated increase in CO2, or we can have just high emissions, or we can have a mitigated scenario. For these three scenarios, we used 5 different global circulation models. Those circulation models, they use the carbon dioxide, but then they compute all of the meteorology, so temperature, precipitation, all these other variables. So 5 GCM. GCMs are for global circulation models. And 3 climate scenarios. And then for 2 times in the future, the near future, so 2030 to 2060, and in the far future, that's the end of the century, we computed what the difference would be in net irrigation requirement. Net is how much water you actually add to the soil, and you don't account for all the losses. On the left-hand side, you see the near future. The right-hand side is the far future for the different rows or the different scenarios. And it's clear that with an unmitigated scenario, we have a lot of a net irrigation increase, and all the stippled regions are regions where that increase is significant. So in the worst case, that's all over Europe. Normally in the mitigated case, it's mainly significant in the southern countries. Now here, this is millimeters per month, up to about 60 millimeters per month. If I put this in percentages, because Thomas already mentioned, we want to see the numbers, percentages compared to the current status, we see that in a case of, for example, high emissions by the end of the century, we would have an increase of 30% irrigation requirement. That's total amounts. Over the years, the variability in the net irrigation requirements will change as well. You see again the same setup of the plots, near future, far future. And what is striking is that in the northern part of these plots, it's all red, and the bottom part, it's all blue. That means that in the northern countries, we'll have a higher variation in our net irrigation requirements, so we'll have more extreme droughts, meaning that we'll have a higher variation in irrigation requirements, whereas in the southern countries, there will be a sustained dry climate. So they'll have to irrigate basically every year, right? So the variation will decrease in the southern countries. Now, I have to make a big scientific disclaimer here. All the results that I've shown are, of course, very uncertain because they come from global circulation models. We see the trend, right? The more we go to an unmitigated scenario, the higher the irrigation requirement. But if you look at the individual global circulation models, there's a lot of variation. So you can have like almost double as much in one model for an irrigation requirement than for the other. And what I've shown you was a median, or here is the average of the requirements. So again, these results depend more on the global circulation model than on the climate scenario itself. So to conclude, in case of a high emission scenario, we'll have 30% extra of net irrigation requirements by the end of the century. This is computed over the summer months, right? The interannual variation will increase in northern regions because we'll have more extremes, whereas in southern regions, there will just be sustained need for irrigation. I hope I have convinced you that we added a really cool new tool to your toolbox, which is AquaCrop version 7 in different applications, and we implemented it into the NASA Land Information System. It's the first crop model that's used in LIS. It allows you to use any type of flexible input, so meteorological forecasts can be changed, soil and crop parameters can be updated. It gives you the possibility to do spatial data assimilation over any domain at any resolution. You can include different types of satellite data. We use Sentinel-1. Now, what can it be used for? For example, for early warning of yield reductions due to drought or diseases, for example. And in the end, we hope that this will help to improve guidelines for water use. Thank you very much.
Well, thanks so much, Gabriel. really fits into the day. And now we go to the last talk of the first block, and I look into Ian, and he's going to talk also about you're going to change the topic.
Yes, thank you very much, Jose. I hope that can be heard adequately by those online as well. This is going to be something different. I realise that I'm the only person standing between you and the coffee break. So hopefully this will provide a little bit of a personal perspective on the nature of this particular project. I think it's appropriate that I give a personal perspective. Thanks to political events, I am no longer European, and I can assure you that I'm not Chinese either. So you could regard this as an independent personal perspective. So in looking at this particular project, it is a somewhat unique funding mechanism. So the European Union has provided 4 years of funding to the researchers in the room, which comes to a close at the end of next month, as you can see by the blue bar here. Our Chinese colleagues, on the other hand, have been independently funded by the Ministry of Science and Technology. And you can see that they started their funding 6 months into the SHui project, and they concluded 6 months early. So what this has meant is it has been sometimes difficult to get thorough engagement between the European Union researchers and our Chinese colleagues, particularly at the start of the project and indeed towards the end of the project. I will say it's been a somewhat interesting 4 years in science. And if we think about the way we were used to working when we had our kickoff meeting in Cordoba and then our second kickoff meeting in Fuzhou in China, extensive use of field work which we used for training opportunities for our early career researchers, all that came to an end very abruptly with this particular virus. So we've pivoted from an almost complete reliance on in-person ways of working through to a complete reliance on online ways of working. And I think as we move towards the back end of the project, we have taken some of the benefits of the online way of working to try and ensure we get greater engagement of a range of partners in both in-person and online ways of working. So what I would like to talk about initially are just a few different models of EU-China collaboration. The SHui project is one particular kind of collaborative model. I want to talk a little bit about the cropping systems we have worked in. You've heard a lot from some of the other speakers already this morning about that. Some reflections on how we communicate or exchange information. The publications that have resulted from this particular project, which for me has been an outstanding level of productivity. I emphasize the word productivity, and I think it's contingent upon all of us to ensure that this productivity actually translates into impact. Hence the need for events such as today where we are engaging with our stakeholder groups. And lastly, I want to consider future possibilities and possibly dare to make some recommendations on how we might use this learning process of the last 4 years to ensure better engagement within the future. So there are a number of different models of EU-China collaboration, and I guess in my career I've benefited from a number of different types, including more unilateral exchanges, and I want to talk briefly about a project I was involved with that overlapped to a limited degree with the SHui project called the SO-REAP project. I want to talk also about truly bilateral projects. One's focused on capacity building, and this is a Newton-funded project by the Royal Society in the UK, and then also reflect on these joint R&D projects such as SHui. So SO-REAP, you will of course realize that the key element when designing a project, be it European funded or other funded, is to get a good acronym, okay? And you'll see considerable agility of language in coming up with an acronym that truly reflects the nature of the project. So At the risk of getting tongue-tied, our project was addressing food security, environmental stress and water by promoting multidisciplinary research, EU and China partnerships. Sow, reap, and I think that gives a nice sort of agronomic context. So the aim of the Sow Reap project was built on the fact that typically there has been substantial numbers of Chinese researchers spending significant amounts of time within countries, within the European Union, within the United States, within the UK. What we wanted to do within the Sow Reap project, and we received some significant funding to do this, was to actually turn that interaction in reverse, to actually ensure that European researchers spent significant amounts of time in China doing their research. And we were very ambitious. We wanted to ensure this at all levels of science, from both early career researchers to midterm researchers to principal investigators. There was, of course, a sort of sliding continuum of funding available in the sense that the early career researchers spent much more time in China than the principal investigators, but there was funding provided at all levels to do that. And we would think, well, why might we want to do this? And there are some clear opportunities to do research in China that are perhaps unique. A lot of the laboratories there are incredibly well-resourced. They have significant infrastructure funding available, usually from the Ministry of Science and Technology. So some of the analytical procedures that I would really struggle to undertake within my own laboratory in Lancaster were very easy, at least in theory, to do within China. I say in theory because often within China the infrastructure is provided, and this might be a state-of-the-art, multi-million RMB facility, but often the level of technical support is not always there. And that's why this kind of funding was particularly attractive to our Chinese colleagues, to actually get technical expertise into some of their laboratories to help them set up protocols and run instrumentation that otherwise they may have struggled to access, even with the best commercial intentions and training courses provided by companies that sell this instrumentation. So we base the projects on existing bilateral long-term relationships. So generally, Chinese principal investigators that had spent either their PhD time or postdoctoral time within European or American laboratories. And I think this was quite helpful because those researchers in China had a very good understanding of the ways of working for European PhD students, particularly. I would say the Sow Reap project had variable success, dependent on the level of engagement between the visitor from Europe and the Chinese host. Typically, we found when our Chinese host had spent time in Europe and there was a good collaboration and communication between the host and the visitor. What we ensured was that there was a cohort of early career researchers from Europe that went to China. They went to different laboratories, mostly in the southeast of the country around Guangzhou. And certainly by having a cohort, it helped our researchers adjust culturally within the country because they could meet up on a regular basis. And what was imperative, as we discovered, was they would not go unless their funding was actually tied to spending time in China. And so this was a mechanism of the collaboration that you might argue was very difficult on the researchers, but was absolutely essential to fulfill the mandate of the funders, which was the European Union. And so I'd like to pay tribute to some of our early career researchers who gained their PhDs by spending at least, up to 2 years in China while being based at a European laboratory. And we graduated a number of PhD students from a number of institutions as a result of this collaboration. So in terms of a bilateral way of working, I've been involved with a project that's still ongoing. Interestingly enough, and this shows the independence of funding schemes, as far as the Chinese authorities are concerned, this funding has finished. as far as the Royal Society is concerned, we have extended this because of the pandemic for a number of years, and we've still got work ongoing within this particular project. So this project was aimed at forming new bilateral relationships, and so I partnered with a colleague who's now the Jose's offsider, principal investigator within China, Weifeng Xu. And so his particular expertise is in the molecular biology of root system growth. I guess my particular expertise, and you may debate this, is a little bit to do with agronomy and crop science. And so we were interested in how the rhizosheath, so soil that adheres to the root system, how that actually forms, and whether that is important in improving plant drought tolerance. The aim of the Newton Advanced Fellowships was particularly to allow the Chinese, in this case, although there are people from around the world who have taken advantage of this fellowship scheme, to come to the UK to develop new project directions. And so what this has meant was that Professor Shui's lab group has spent time in my lab for up to 3 months to acquire new skills such as high throughput measurements of plant hormones, quantification of rhizosheath development. Again, I think this project has been successful, but I would stress there has been variable level of engagement according to the particular researchers that have actually been placed in my laboratory. It's interesting that if you go to Professor Shui's laboratory, there's one particular form on the wall that indicates the timing at which each individual researcher in the laboratory is expected to produce a new paper, okay? Now, science doesn't always work like that in my laboratory at least, and you certainly want to cultivate significant independence of the researcher and get them to develop their own ideas. So I think different levels of independence versus, if you like, command management contribute to the level of engagement you might get from a visitor coming to your laboratory. Nevertheless, I think it's been incredibly successful in developing this area of research within his laboratory, and we're hoping for continued funding of this via another mechanism. This, of course, leads to our own project, the SHui project. Again, you'll appreciate the relationship between the acronym and the title of the project. And here we wanted to exploit existing and also form new bilateral relationships. I think this has been quite tricky because of the funding mechanism within the Ministry of Science and Technology. For them, it has basically been business as usual, relying on existing work that's been ongoing in their laboratories, but supplemented by this additional funding to allow Chinese researchers to participate via travel and subsistence funding to engage within the project. As you would expect, if the principal funding mechanism relies on travel and subsistence, and with COVID preventing that as being a possibility, I think it's been more difficult to get genuine active engagement of our Chinese researchers, particularly during the time of the pandemic, particularly in the cases where they've not been able to come into their own laboratories to work, let alone travel to Europe to work with us. So there has been, I would consider, much more engagement via online platforms. You can debate just how useful some of this online engagement has been. Nevertheless, as the pandemic has taken its course, there have been opportunities for research exchanges. Often these have been funded by other sources, and I think they've been really valuable. And I would just like to pay tribute to a couple of early career researchers from China that have come to my own laboratory over the course of the last year or so. One's now doing her hotel quarantine back in China, having escaped from the COVID-ridden plague of the United Kingdom, okay? And she's at the end of her 3-week hotel quarantine back in China. So these two researchers came to work on projects related to some of the objectives of SHui, looking at a form of irrigation known as partial root zone drying, looking at the relationship in rice between irrigation frequency and rhizosheath development. And I think these researchers were very brave culturally in the sense there is always a significant level of personal engagement required to uproot yourself from what the ways of working you know and go to a different laboratory, particularly when you don't understand the language very well. I think they've been even braver when you consider the rather different approach to COVID regulations in China and the United Kingdom. So, full credit to them, and they've done some interesting work. I'd now like to turn to cropping systems, and you probably can't see it in this map of China here, but there's some information provided on the major crops within China. Clearly, as we go from the southeast to the northwest, there's a significant water scarcity gradient, and so a lot of the European or Mediterranean cropping systems that we might be working on sort of fall within this sort of heartland of China as we go from the southeast to the northwest. Of course, rice is always going to be a crop of significance to Chinese researchers, and obviously it's quite difficult, at least in the northwest of England, to provide the sort of facilities you would want for growing rice crops. We have managed to do that with temperature-controlled greenhouses. There are certainly some similarities where I think there's been good translation of results between the EU and China, particularly in relation to cereal rotations. In some cases, our Chinese researchers, logically enough, want to work on important local problems, such as concerns about water scarcity for rice cropping. It's not always been possible within this project to pair partners with the same field-based cropping systems, but we've tried our best to do that. Communication is I think, always a challenge, even within the European Union. Our language skills do vary. I think it's exacerbated, particularly when we work in countries like China. To a large extent, this has been mitigated by the newer generation of Chinese researchers, particularly those that are early in their career, that are highly motivated and want to maximize the gains in terms of acquiring technical expertise and different ways of working from being engaged in a European Union project such as this. The other element that's challenged us in terms of communication has been the project website. I think we were perhaps a little naive, thinking we could have one website that would be compatible with both English, Spanish, and Chinese as the three main global languages worldwide, and I apologize to my local hosts for making that particular statement. As it's turned out, we quickly needed to adapt our ambition to ensure there was a Chinese named website for our project, because within China, our European Union website domain was often blocked. I'm not certain why. I would have thought that the content we had provided for the website was not likely to be blocked, but there were challenges of operability here. Certainly, we who are at PI level recognize that when we go to China, there's often considerable attendance by early career researchers, whether that's voluntary or compulsory. Perhaps I haven't really got to the bottom of that. But I think what's been unique about this particular project, and I think it's been part of the transition to working within a pandemic, has been that online training environments can really enhance participation within the project. So within the project, we've had a series of webinars and other online ways of working, and I realize a number of you have contributed to that. And this has been particularly valuable, and I think something that in future our Chinese partners will expect. As long as we can timetable the meeting at an appropriate time, there is the opportunity to ensure that those that can't attend in person can actually attend the meeting. Having said that, I still think there's an important role for bespoke, in-person, somewhat more technical training. So perhaps the first example post-pandemic that we managed to achieve at Lancaster in that was we got an invitation from Delta T Devices, who manufacture some of the instrumentation that Juanjo was talking about this morning. And we set a series of objectives that were sort of quite technically focused to calibrate and maximize performance of certain instrumentation that Delta T had provided, understand the theory and practice of different sensors, and run bespoke software to visualize and analyze the data from some of these sensors that were provided. Now, with this particular workshop, we were limited by current COVID regulations in Lancaster to no more than 12 participants. Our Chinese early career researchers had joined the lab by that time, so they were able to participate. And what was particularly interesting was they said that in China, we would not have the opportunity to do this. If there was such an event scheduled in China, there would be 100 or more researchers there, and we wouldn't get the care and attention to detail that such a bespoke course was able to provide. So some learning there. Publications, I think this was one of the first. Jose led the basically setting out the ethos of this particular project. This was one of the first of many. And it's interesting that our two groups of researchers within the European Union and China have basically been very loyal to their funding source when they come to publishing their work. There are, I think, 5 papers that mention both funding sources. The other thing that's quite interesting is when you do an analysis of the areas of which this project has published in, there's more than 50% of the publications from the EU are sort of looking at the bigger picture in terms of environmental sciences and water resources within China, and possibly this reflects the productivity of our coordinator in China, Professor SHui. There's huge emphasis on plant sciences and also agronomy. So some differences there, but I think we have attempted to try and ensure complementarity of approaches across the EU and China. So my final slide, because I can see they're preparing the coffee out there for all of you. I think what's critical to ensure success of projects like this and is to ensure that they do run for the same duration and there is much more equitable funding. To some extent, we have capitalized to a large extent on collaborating with very successful Chinese researchers that already have substantial Ministry of Science and Technology or other ministry funding in their laboratory. This has worked to some extent, but clearly we are piggybacking on existing funding mechanisms that they have, and what that has meant was that sometimes it's more difficult to change the type of research that might be done. I think what will be really valuable in the future, and possibly such a mechanism exists, is for there to be flexible and competitively awarded funding allowing true bilateral mobility within specific projects such as this. So clearly, the Chinese early career researchers that came to my lab were funded by other sources, Chinese Scholarship Council or provincial funding. I think at a European level, if we're going to continue to engage with China in the way that this project, and I know there are other projects in the past and others will in the future, I think there needs to be a specific funding mechanism of the kind that we employed within the SHui project to ensure that if European researchers want to go to China, there is the opportunity to put in a specific bid and apply to work for 6 months or 12 months in a specific laboratory in China. And lastly, I think, and any project is a learning process, there needs to be much greater awareness and perhaps alignment of funder expectations. And I think what's possibly the best way to indicate this is this true level of impact versus publications. I think within the European Union, given the nature of the funding that is designed to try and provide answers to specific environmental challenges, impact is always emphasized. That's why we have meetings such as this. I can remember even before the SHui project started, going to China as part of another visit and talking to a group that was going to be involved in this project. And they gave a very nice presentation about their work. And my first question was, well, this is fantastic. How many times do you meet with farmers to tell them about this? And there was large discussion, lots of getting out the phone, making sure that the translation was in fact accurate, okay? And the ultimate answer was, oh, we haven't told farmers about this work yet. And hopefully with projects such as this, it provides a roadmap forward in terms of indicating how important the work that the research work that is being undertaken is in terms of informing and perhaps altering farmer practice. Because I think that's what the mandate for this particular kind of project is. I would emphasize that, you know, there is a lot that we also within the European Union can learn from our Chinese colleagues in terms of farmer engagement. So certainly within this project there's been a large number of events, perhaps fewer than we might have expected because of the pandemic, where our Chinese researchers have not just talked to, you know, half a dozen farmers, they've talked to hundreds of farmers at a time and demonstrated techniques that will address problems of soil degradation and address problems of water scarcity. So thank you very much. I hope that's been an interesting reflection. And do tweet or Facebook or whatever you young people do when it comes to this particular project, since we're in the room together. So thanks for your time.
Well, thanks so much, Ian, and everyone else in this morning.
Okay, good morning, everybody. I have to apologize. First, my talk starts with an apology because I forgot to mention also Julian. Sorry for this. So I skipped this part because it's already it has been already addressed during the first part of the discussion this morning. I just want to add to the major global societal challenges the agricultural sector is facing, the management of natural resources is facing during this harsh time, I would say. Apart from the water scarcity, the problems with the soil erosion and so on, and the climate change, of course, I would add other two major problems that we are experiencing in Europe, but I would say worldwide. First of all, there is a kind of trade-off between two main processes: the intensification from one side of the farming system, of course, and the agricultural abandonment, the abandonment of the land. And this is a very crucial point, and from these there can emerge threats, but also opportunities that should be somehow addressed in a policy consortium. And another problem we are dealing with is the elderly index that is going worse all the time. The age structure of the European farmers that are increasing the polarization of the agricultural structure, and is making even worse the concentration phenomenon, the concentration of the land use. So, and the other part, we have experienced such a problem during the COVID crisis, the urgently need for hired labor, both skilled and not skilled, in the agricultural sector. The policy context, very few words. We are in the phase of the new programming phase. So the new policy, the new agricultural policy will enter into force in 2023. There are two main important changes. From first of all, the mechanism. The new delivery model, so the focus shift from the results to the outcomes. That is a very important change in the functioning of CAP. So the member states have to provide strategic plans, and then the other important changes is the introduction of a new eco-scheme, a new tools that together with the conditionality and together with the environmental and climate friendly measures and investment should aid the agricultural sector, the European agricultural sector, to address the Green Deal targets, and mainly those stemming from the farm to fork strategy and the biodiversity strategy. Another point that I would like to stress is the changing context. SHui project has witnessed two big problems along its duration: the COVID and now the war. And these are the words of the EU Commission that in the revision of this strategic plan is saying, okay, pay attention, we need to refocus our decisions because we need to counteract somehow this new situation. So we need to take in account the link between climate action and food security that is becoming a very crucial issue. So the stress has to be on increasing the sector resilience and to reduce the dependency on fertilizer use and scale up the production of renewable energy without undermining food production. That is a very important point to be addressed. And then trying to apply sustainable production methods. So this is the scenario, let's say. SHui project has provided, as already mentioned in the first part, several, a very huge, I would say, suite of technologies and tools to address the optimal use of scarce soil and water resources. And this has been done, it has been done at in-field level and at larger scale. And also this analysis has embraced also the social and economic parts, trying to provide an overview, a very complete overview to the stakeholders, addressing both technical and economic aspects. And the project tells us that best management practices can provide, although with some uncertainty, like Thomas mentioned before, and I think it's an important aspect that you mentioned before. But in any case, best management practice can be can provide good tools to address the problems, but we have to take in mind that there are trade-offs between different ecosystem services, so the best management practices should be adapted to the local conditions, and also that we have to exploit the synergies between different sustainability goals. So we have to take in account that the farm can be, or the landscape level better, can be the place where different sustainability goals should be how to say, managed in synergies, not in conflict. So very few insight that I hope that will be useful for the round table. As Gianni has said before, we have seen that there are economic efficiency gain along the economic gradients of farms, but not environmental, actually, not environmental gains. And this means that, and confirm what I was saying before, that the smaller farms are less competitive than the larger one, of course. And this is a very important point because their role in managing natural resources and provide economic and social basis for the local communities are endangered by their market marginality. So I know that is quite trivial, but I think it's important to stress that diversification and alternative economic exploitation of natural resources has to be pushed and boosted in order to overcome these problems. And the focus group revealed the importance of strengthening farmers' position within the food chain. They are squeezy. the squeezy phenomenon is already ongoing, and this, and particularly in this moment when the costs of the input are growing a lot. If we don't have any control on how the value is shared among the different actors of the value chain, the cost of this increase will remain only on the shoulder of the farmers, with the danger for the sector. So one of the solutions can be, of course, the short chains and the increasing use of organization in order to overcome the monopoly of the that is typical of the distribution and the last part of the food chain. Another aspect that emerged from our analysis is that the labor and the other costs are driving land use changing. So, for example, in Spain, the stone trees are replaced by olive groves. And this is an important issue because we are experiencing how the linkage between agricultural sector and industry sector at national level. So if we want to provide this link, and we want to make this link functioning in the future, we need to pay attention at this kind of substitution at the local level. So we need to pay attention to these land use changes. Other aspects have to do with for example, lack of flexibility in water allocation. We were talking before about the lack of management at landscape level. I think this is a very important aspect. The possibility to have a landscape approach instead of just managing an allocation based on first come, first allowed. Then very for some farmers have highlighted the importance to have affordable, in affordable way, critical inputs such as, for example, the crops that have to be used for cover crops, or, for example, the availability of technologies that are tailored to the local conditions. So this is another important aspect to be addressed. So the importance to have technologies that are well fitted to the local conditions. And this is another important that involves an idea of innovation that take in real consideration the local needs. So the operational groups that are instruments that have been introduced in the last programming phase should be enhanced, should be promoted in order to grasp the real needs at the local level. Another aspect, very few seconds. Stakeholders have emphasized that the farming system needs time to adjust to the new conditions. So maybe the policy programs are sometimes too short. And also that administration, apart from lowering the administrative burden that is an issue all the time, but the administration should set a clear policy, clear rules. The example is, very typical example is the use of glyphosate. So there is a need for a long-term perspective, and for example, the eco scheme are taught as a 1 year scheme. So this can be a weakness. So the land managers need predictability and need a long-term certainty in order to implement measures optimally and invest as needed. Sorry, it's not really clear. Polarization, the structural polarization. Lots of very small farms, big farms from the other side. In this case, cooperative approaches can be one solution. Collaborative management approaches can be a solution that can somehow can address this problem. Collaborative agri-environmental management has been introduced into the previous, in the actual programming phase, but should be encouraged more, because can provide environmental benefits, because the ecosystem services are acting at catchment scale, at a larger scale than not at the farm scale. Economic benefits are evident, because if there is a management at landscape level, cost can be shared by the farmers. So this can be a solution, or at least a way to address the problem of economic dimension, little economic dimension. And also there are social benefits. Trust, relationship, exchange of information, peer-to-peer exchange. So it's, in my opinion, or at least the literature tells us that the collaborative management has to be exploited more in order to address the macroeconomic problems of the sector. Some insight coming from the papers that you have are the results of that are synthesizing the results of SHui project. So in some study areas, there are the less experienced farmers are still not applying the BMPs, the best management practices, because they feel the complexity of the best management practices compared to the conventional ones. In this case, there is a scope for improving the training of younger farmers, and linking maybe them to the more experienced farmers. This was introduced into the last programming phase. This should be or could be reinforced in order to promote these linkages between generation, among generation. And for sure, the on-farm demonstration is a very good tool. The peer-to-peer exchange has to be promoted more. I already expressed this idea to capitalize on and exploit the results of the operational group, and also boost up their new settings in order to foster, to aid the co-creation of innovative solutions that can be best fitted to the local conditions. And also the soil and water conservation can be proposed as a business model, especially to young farmers. So change the narrative, say that we don't need to maximize production, but we need to decrease the cost of production. So change the mindset. And it's the last one, I promise. The other few recommendations. Provide incentivized practice that contribute to a holistic transition towards more sustainable farming, and not just promote simple efficiency gains. It means not move from an environmental efficiency perspective to a sustainable one. It means address not only the economic aspects, but also the environmental aspects, but also the economic and social ones. And implement multidimensional sustainable schemes. It means not just one best management practice, but a different management practice that together can exploit synergistic relations. And of course, for the problems I mentioned before, the payments should be accurately proportionate to the costs farmers are facing in order to implement this measure. And of course, especially with this new approach foreseen by the new CAP, there is a need to avoid overlapping between the schemes. So trying to assure the correct functioning of the different schemes at farm level. So that's all. Yeah, this is. Thank you for your kind attention.
Thanks so much, Rosanna. And now, if you kindly can come to the place that I already see you before. Well, when my friend Peter told me 20 hours ago that I need to chair this round table, I'm not an expert in irrigation, just a humble expert in soil and water conservation, whatever that means. I started to be worried and read. One of the things that is pretty clear, not because of that, when you work in agriculture today, there are 2 or 3 issues related to water that are happening simultaneously in different perspectives. One of them, I was involved in the Spanish plan of the certification some months ago, is that in agriculture in many countries, not only the Mediterranean, access to water can make the difference to a farm as a business. Simultaneously, it's a resource that is finite, and there are many issues related how we handle that. And what has striken me in the last months, I start to read out of curiosity, is that the interest in irrigation is showing up in countries and places that you never realized it was happening. Just read the other. Delaware is a small state in the eastern part of the USA, but they increased the irrigated area from 2.5 to 10% in 10 years. So it's not going to be Almeria or Murcia, but it tells you something. So the idea of this round table is to take advantage of these 4 fantastic members of the panel that we are going to enjoy. And the first, I'm going to give 5 minutes, 5, 4, 3, whatever you want, to introduce yourself and raise what may be a key point on the overall issue of how to optimize the use of water for agriculture in a broader perspective. And I'm going to start with Miguel Barnuevo. He comes with several hats from the community of irrigators or Unión de Pequeños Agricultores, and you can introduce yourself, Miguel, and take the word.
Okay. My name is Miguel Barnuevo. My father has studied here in Louvain 60 years ago, in the 50s. So I'm not so far from my home. I'm 58 years old. I studied in Madrid, and now I'm president of Asalbac. It's an agriculture conservation association in my region, but I'm also vocal of the National Association of Conservation Agriculture. And I'm always working with the Junta Central de Regantes de la Mancha Oriental. Is the organizations of irrigation farmers in Albacete. We totalize 120,000 hectares. Okay, I've been also president of the water jury to control the farmers 10 years ago. And I've been working in the last months in the hydrologic planification with Anna. Anna is our opposite in the water problems in Albacete. And I've been working also with an almond company, and I collaborate with UPA in some experiences project. My experience, I began to be farmer in the 80s, and my experience is I began with no tillage in 1993, and in dry plots. Now I began with irrigation plots in 2000, and my whole farm is working in conservation agriculture. I don't plow. In 20 years, I haven't plowed my land. And with this experience, I've been working, now I'm working to other farmers. I make the seeding service in no-tillage system for 1,000 hectares. So I have a little experience with corn, barley, and so on. A little experience. They have make a resume. I have to note to the resume. I've been impacted with the strategic plans, and one of the farmers are very much worried about the new strategic plan and the eco schemes, because it's a new way to see farming. I've been working with the ministry, our association, in the eco schemes lines, and in Spain, I can say that there are 8 lines, and 3 are no tillage cover and 2 for cover crops. So the line in Spain is going to conservation agriculture. We have to cover our soils because we are losing our soils. We have a big problem with erosion. And in water, my experience is I'm a farmer who comes from a typical situation in Spain: drought land, low yields, low expectations, and I became a irrigation farmer in the 90s. So it's another vision of farming. The future in our country, we need irrigation. The problem we have is now we have climate change, we have droughts longer than before, and we have to manage the water because we are reaching a limit of use of farmers. The problem is there's no more water, and we are reaching our top level of surface of irrigation. So that brings out us many problems because there are little fights within us. We have to make an effort to manage this situation because in the next years we are going to have big problems. One of the questions for me is more important to manage the soil than the improvement in the irrigation systems. Because when you make a good manage of soil, you improve more than you can believe your yields, your soil conservation, the inputs, your costs are lower, and my obsession are not the yields, it's the conservation of my land for the next generation. Okay, thank you.
Thanks so much. Now, I can give the word to Tim Hess, who also comes of 2 or 3 qualities, right? You have with 2 hats at least today.
Yeah, thank you. I don't have quite as many hats as but I'm wearing 2 hats. I think it's 2 hats. I'll let you know at the end. So thank you for inviting me along today. My name is Tim Hess. I'm a professor of water and food systems at Cranfield University in the UK. And I've been there a very long time, as you can tell by my grey hair. And I guess I've had a very varied academic career at the university there. But the common theme has been the relationship between agriculture, food production, and water. So I started my research career actually working in flood risk management and agriculture, and about the impact of flooding on farmers and the effect of excess water on the economics of farm businesses. And I still have an interest in flood risk management, and particularly about how land management can influence flood risk management. So I was interested in the presentation earlier about impacts on runoff generation and how we can use agricultural land not just to produce food, but also to manage the hydrological environment. And over time, I gradually started moving away from working in too much water to what happens when we don't have enough water, and started getting involved in irrigation and irrigation management, and worked a lot with UK farmers on irrigation management over the years. But also, most of my international experience has been in Africa, and particularly Southern Africa, Eastern Africa, and some parts of West Africa, and then a few other places around the world, but mostly in Africa, and also working quite a lot with the commercial horticulture and plantation sector. So not so much working with small-scale farmers in Africa, but working with sugarcane industry, working with companies that are producing export vegetables for the European market. So people who are irrigating on a very large scale. And more recently, my interests and research interests have been moving more towards how we can sustainably feed ourselves, whether that's on a national or a global perspective, particularly in relation to water and the impact of food production and food consumption on the water environment around the world. So we've been working with water footprints, and particularly looking at how consumption of fruit and vegetables in the UK is impacting on water resources around the world. We import 70% of our fruit, we import 50% of our vegetables, and we import those fruits and vegetables from countries which are dry. So large amount coming from Spain, but also from Israel, South Africa, Chile, Morocco. So the one common factor those countries have is that they're all very dry countries. So what impact are we having through our fruit consumption on those countries, but also to what extent is our supply of fruit vulnerable to drought and water scarcity in those countries? So how is our diet vulnerable to those countries? So my academic career has sort of covered a very wide range of topics, all of which have come up in the presentations this morning, which has been fascinating for me. The other hat that I'm wearing today is I was invited to come along to represent the UK irrigation sector. And I thought it might be useful just to say a little bit about irrigation in the UK. Because when I ask people to picture what a farm in UK looks like, everybody thinks of something that's very wet. We've got problems with mud. We've got problems with tractors getting stuck in the field because it's too wet. And they don't think about irrigation as being part of the UK agricultural system. And you're largely right, but occasionally, in certain places and certain times, irrigation is absolutely critical. Our water abstractions for irrigation in the UK accounts for about 1% of our annual water abstractions. They're absolutely tiny on a national scale. Most of our water abstraction is for domestic use and for industry. And on average, that a total abstraction is about 180 million cubic meters of water per year. That's probably less than your farmers in your one region of Spain is using. But if that was the end of the story, then I could just leave the room now and get the Eurostar and go home because I wouldn't have anything to contribute. But actually, the UK irrigation sector is really important for our vegetable production, particularly potatoes and root vegetables. Almost 80% of our irrigation goes on to potatoes or carrots and other vegetable crops. Very little of our cereal crop is irrigated, although this year I've seen farmers irrigating cereals because it's been dry, and of course the price of wheat has gone very high. So farmers who've got water and got equipment have been irrigating their cereal crops this year, but that's quite unusual. Most of it is going on to, say, potatoes, vegetables, and high-value horticultural crops. But geographically, that irrigation is very much concentrated in one region of the UK. So about 80% of the irrigation is taking place in the eastern and southeastern part of the UK, which is the driest part of the UK. And I remind people that Eastern England has the same average annual rainfall as Jerusalem. Now, it's slightly misleading because Jerusalem gets it in one season. We get it uniformly distributed over the whole year. But around 600 millimeters per year is the average annual rainfall in Eastern England. So it is a dry part of the world. So we're growing our irrigation-intensive crops in the driest part of the country. And at some times of the year, and I imagine this week will be one of those times, actually abstractions for irrigation is the major water abstraction in the eastern counties of England. So although across the whole country, across the whole year, it's only 1%, but sometimes it can be the biggest abstraction. So it is important to UK agriculture, it's important to the UK economy, and it's important to UK farmers. What's challenging the UK irrigating farmers at the moment is about securing their share of the water and their access to water. Perhaps because agriculture is only taking 1% on average, it has a small voice. It's not able to defend its requirement for water on the national stage. That eastern part of England, where most of the irrigation is taking place, the catchments there are predominantly classified as either over-abstracted or over-licensed. So that means that either we're already abstracting too much water for what is sustainable, or if everybody was to abstract everything they have a license to abstract, it would be unsustainable, but not everybody is abstracting it. So that means it's very difficult for farmers in those regions to get a license to abstract any more water or to expand their business, because they're right at the limit. And the Environment Agency that managed water abstractions is actually trying to remove licenses from some farmers in some areas to reduce the abstraction, particularly during dry periods. The environmental impacts of over-abstraction are unacceptable, and so farmers who are not using their license or not using all of their water are seeing that they're having their licenses taken away. Climate change, of course, is a consideration. The projections for climate change for south and east of UK are for hotter, drier summers and wetter winters. So two problems, needing more irrigation water in the summer and causing more runoff in the winter, leading to more flooding in the winter. So perhaps the double whammy coming from the climate change projections. On a national scale, the key question in relation to climate change and water demand is not how much water we need per hectare, but how many hectares of crops are we going to grow and where are we going to grow them. And actually looking back over the last 20 years, total national demand for irrigation water has gone down because we are eating less potatoes, so we're growing less potatoes, so we're irrigating less potatoes. The national diet has become more cosmopolitan. We don't just eat fish and chips now, we are eating pasta and we are eating rice, which we are importing from other parts of the world. So actually our demand for irrigation has gone down. But if we start to produce more of our own potatoes again, more of our own vegetables, more of our own fruits, then the demand for irrigation will be going up. And there's some interesting sort of international questions about should we be reliant on water resources in other countries to feed people in Britain, or should we be using our own water to do that? But the other big challenge to the UK irrigators is demand for water from other sectors. So not only is the eastern and southern part of England the area where we have most irrigation and most water demand, but it's the area of greatest population growth and new housing development. So that there's a potential conflict between water supply for domestic production, for domestic use, for houses, taking away water for farmers. Of course, to politicians, the housing and the population growth is much more powerful than giving water to farmers. So in reaction to that, farmers are starting to work together, to collaborate together, to have a stronger voice, to defend their position, but also to share access to water resources. And we're starting to see shared reservoirs, farmers sharing licenses, being able to give excess water to neighbours when they have too much, or borrow water from neighbours when they have too little. So traditionally, farmers have irrigated on their own, but now they're starting to collaborate, really to defend themselves against these challenges of losing water.
Okay.
That's a bit of context.
Thanks so much, Tim. And now we have the word to Professor Dirk Raas. He's in the table for several reasons, but he can explain by himself. One of them is his broad expertise.
Okay, thank you. So I'm Dirk Raas from Belgium, actually, from the University of Leuven, and from the same department as Gabrielle, actually. But meanwhile, I'm already retired, but I still have some assignments at the university. So I was a professor teaching irrigation, although like England, we don't have much irrigation in Belgium, but I studied irrigation in Italy, in Bari, and I was also, I spent some 3 years in Algeria, working there at an institute, and then 4 years in Senegal for managing the water at the Senegal River, actually. So I have some experience in irrigation. And then at KU Leuven, at our university, we have our regular students, but we also have an international master, which is UPWare, Water Resources Engineering. Together with Brussels, we run that. And then we have students from all over the world. So, and then I got also a lot of projects all over the world with different funding, most of them always in irrigation and most of them in the dry areas. Maybe my second hat, if you like, is that I also work close with FAO, with the Food and Agriculture Organization of the United Nations. And FAO, as you know, is not a research institute. But FAO was looking for a model, actually, to giving advice to farmers when there is water scarcity. So they would like to have a model which can easily produce guidelines to improve the water productivity, or just give guidelines for irrigation scheduling, or also for effects of climate change. So FAO set up in the early years 2000 some meetings with a lot of crop modelers from all over the world, and with other scientists involved in irrigation. And out of that came then the idea, so let's make because there are a lot of good crop models actually, like TSAT, CropSys, TWOFOS, whatever, but all of those are mainly research models working by a research institute. And FAO said we don't need a research model, we need something practical actually, but which is of course strong, which has a strong science in it. Soil sciences, irrigation sciences, plant sciences, all that in it. So with some people from different universities, so we developed then the aqua crop model, and which was then for FAO actually. And the good thing is that FAO used that model in a lot in its projects and also in training. So we went to different countries to give training, and the training is always with the local people and with the people from ministries, and these are not researchers, so you spend some time in explaining how things work, because they have no idea about modeling, but they have a lot of questions about the field. And that is a very good thing, because that helps us to develop, and I think also Rosanna mentioned it, the model becomes more and more fit to the local needs actually, because you can have a nice solution for something, but which is not practical, it's not good. So with the help of the local knowledge that was brought in the model, but also of course with the help of PhD students, a lot of information and field experiments were set up to improve the simulation actually in the models. And now recently the group van Gabrielle put it made it a regional model, because aquacrop is a field model. And so where it can be linked with other models and new applications becomes available as well. And that will be discussed, as Gabrielle was saying, at the end of the month with FAO. So how are we going to distribute that actually? So that's me.
That's fantastic. And now I give the word to Ana Ferrer. Sorry for not remembering. She comes also from the eastern part of the country, and you can introduce yourself, Ana, please.
Thank you. Yes, my name is Ana Ferrer, and I'm a lawyer, and my professional career has been linked from the beginning to the world of water, advising irrigation community. I am a member of the legal advisory body of the National Federation of Irrigation Communities. That is a non-profit association that gets together more than 700,000 irrigators and more than 2 million hectares, representing 80% of the Spanish irrigated land. And since 2005, I have been working in La Acequia Real del Júcar, where I carry out management and administrative functions. And La Acequia Real del Júcar is one of the oldest irrigation communities in Spain. It has been managed water for more than 750 years. And it's taking part of the community more than 25,000 irrigators from different municipalities in the east of Spain. And also the irrigable area is 20,500 hectares of different crops, rice, citrus, fruit trees, and orchards, traditionally watered by flooding. But in the 2000 years, we started our modernization plan, switching to flooding irrigation to drip irrigation. And now we have more than 6,000 hectares, representing 36% of our irrigable area. And I wanted to mention 4 of the major advantages of our modernization. That is water safe, of course. We have reduced in more than 180 cubic hectometers a year in a system, in a very vulnerable system, that we use the savings to correct the imbalances between valuable resources and existing uses, and also to reduce the impact of droughts. But we are able to reduce up to 60 cubic hectometers more as our modernization process progresses. And that savings are reserved in our hydrologic plan to Albufera, a natural park. It's a natural reserve, including as a Ramsar site in the list of wetlands of international importance. So we have a modernization committing to the environment. The second advantage of our modernization is that it's a modernization without energy consumption, because the pressure that we need, we get it by gravity, because our head reservoir is located 40 meters above our irrigable area. And in addition, our fertilizers and irrigation manager centers are pressured by photovoltaic energy. And the third characteristic feature or advantage is that we reduce the use of fertilizers and herbicides by more than 50% compared with flooding irrigation. And that contributes to reduce the effects of diffuse contamination in underground water in a vulnerable area. And in addition, we have more than 500 clean water points to allow the development of organic agriculture. And finally, it's a modernization based on technical and digitalization, because all our infrastructures are connected to an operations center via fiber optic, Wi-Fi, and radio to manage and control all the system. Our technicians they do their fertilizers and irrigation programs, taking in account the information provided by conductivity and humidity sensors, and of course water meters. Invoicing is based on a binomial system, a binomial tarifa, according to the surface area of each plot and its consumption, and we penalize overconsumption. And we count with the support of the Polytechnic University of Valencia, and also with a Valencian Institute of Agriculture Research, and of course with the experience of our trusted suppliers to keep on improving. And all these tools managed by the irrigation community allows us to optimize the use of water in our agriculture and to contribute to improve the environment in our irrigation area.
Okay, thanks so much, Anna. And your talk raises to the first question that we were preparing for the roundtable for you, and is up to what point the technical fixes or the technical solutions can, what fraction of the problems related to water can be solved only with technical solutions that are great, and what part remains in other fields like governance or other issues? So I think we all would like to know what are your thoughts on this. Who wants to start?
I think the main problem is governance, first. Because now in Spain we are arriving to the top of consumption of water in irrigation. There's no more water. Technically, we are good farmers. But the question is how many water, how many water have you had in your license to irrigate? Because it's not the same farming with 1,000 meters hectare than farming with 5,000 meters hectares. The investments are there, but you are not going to make an investment for 1,000 meters hectares. You're losing. The second question, technically we are arriving with sensory remote sensing, and we are arriving to see where we are more efficient or not in our plots. This is the next desafío, the next challenge. Because we are reaching very good results with the recommendations of the agronomic institutes, and the recommendations are very good now, are very, when you know your efficiency system, when you know the efficiency in the system, we irrigate very well. But the next challenge is I have seen in last years that with the remote sensing maps, we are seeing that we are spending water in some parts of the plots that we don't need to irrigate so much. We have to spray the water better in the plot. We can save with these techniques, I think 10%, 50% of water, and make them more profitable. Because one of the problems now is our costs. They are very high. You know, the cost of energy, the fertilizers, pesticides has grown twice, okay? Now, to make farming is very risky, and more risky in irrigation farming, because the risk is double. My experience this year is I have seeded less hectares, in corn hectares in Albacete, because the farmer has no the money to pay the energy. He wants to seed, but he doesn't want, and the risk is very high. I'm very worried about this because I think we had a problem of food security in these moments, mainly in Spain, because we have to import many tons of cereal each year to food our animals, pigs, corn, cows, etc., sheep. And we are now in the sites where they are fixing the prices, Las Lonjas. They are very big discussions of our prices because too high prices are not, the people can't buy with these high prices. So perhaps in irrigation systems we are reaching in Spain a good governance. Now we are discussing with the government how many water is for farmers. the discussion is very hard because in Spain, one of the problems was that the rivers were not flowing. The humid areas were dried, and now the society and the government wants to keep these areas more natural and with more water. Rivers needs water, these areas needs water, but that means that the farmers, we are going to have less water. If you are not organized, it's war.
Yeah,
That means war between farmers and between administration.
It looks like you pinpoint something similar to what you said in southeastern England. And do other of the experts in the table, any of you, thinks also like Miguel that governance is a major issue or need to be balanced, or you did, for instance?
Yes, I think so, because technically it's a little bit like climate change. So technically we know how to solve it, actually, but it is the policy, the governance, who has to make the decisions, and they are hesitating to do that because it might hurt people. So technically, and for water, there was a very interesting, I think it was you presenting the deficit irrigation. So it's a very interesting, and it is proven, and I would like to see your work as well, that with the same amount of water, you can easily produce 40–50% more food with the same amount of water. But the problem is that a farmer is not interested in deficit irrigation, because a farmer is interested in the production of his field, and he would like to have the maximum production. He never go for deficit irrigation because he will have a lower production. So you have to bring the farmers in one way or another together, and as a scientist or researchers, we cannot do that. So it is somewhere a government, local government or whatever, who should bring the farmers together and said, in this community, this is the amount of water we have, so let's divide it so that we can produce 40% more food, so that the whole community will benefit from it. So I think technically they are not, they are still, of course, challenges, and there are always new things coming up, but it is, you need to implement it. And if you may allow me, that is also a little bit the good thing about aquacrop, actually, that it is not a research model as such. Of course, there is a lot of science in it, and thanks to researchers like Shannon and Louise, we bring in new things, and Gabrielle now made it also a regional model. But the good thing of FAO is that they give the training always in request of the country. So FAO is never going to make a project, it's always the country ask for a project, actually, for a practical problem they have. So, for example, we had a big study in West Africa about the effect of climate change. They wanted to know that, and therefore aquacrop we used aquacrop. And the people following the training, these are not researchers, these are not people from the universities, these are people from the Ministry of Waters or of Agriculture or things like that. So with the training, we give them tools, actually, and it's up to them then to apply them. So I think that indeed the main problem is always, how are you going to implement it? And we as scientists cannot do that.
It looks like in the UK, going back to this governance key issue, I don't know if you agree that that's the major one. It looks from what you said that it's basically the reorganization around the water rights is made by farmers by themselves, or is the government try to lead that, or?
Is technology the answer? Is governance the answer? They're both the answer, but they're answer to different questions. And I think one thing we always need to be very careful of when we're talking about problems of water scarcity is to actually unpick what the question is and who is it important to. So maybe if you're a farmer and you have a fixed supply of water from a reservoir, which is not enough to irrigate your area, then a technology answer to make you more efficient may be the perfect solution. If the problem is that at the basin scale there's not enough water to go round, then technology is not the answer, and it's governance that's the answer. And the layers of the different systems of technology, management, and governance all have to operate together. And I was just going to give an example of how technology may not always help. I was just a couple of weeks ago on a big commercial vegetable farm in West Africa, where roughly half the farm was centre pivots and half the farm was drip irrigation. And on the centre pivots, they are putting about 30% more water than they need to put onto the crop. On the drip irrigation, they're putting about 50% more water than they need to put on the crop. So they're over-irrigating much more with the higher technology, so-called more efficient drip irrigation system than they are with the pivots. Because it's the way that it's being managed, it's the problem. And the efficiency is entirely determined by the management system, not the technology. So, yeah, and now putting that question back into the UK context, yes, it is governance which is the big issue at the moment. But it links into technology and efficiency and management as well, because in the way that the Environment Agency is approaching the reform of the abstraction system, they are putting pressure on farmers to demonstrate that they're using water sensibly in order to be able to renew their irrigation licenses. So farmers are having to demonstrate that they are using the right amount of water, that they're scheduling it properly, they're using appropriate technologies to then be able to renew their license. So the governance system is then actually forcing the technology system to improve as well. So it's all linked together.
In Spain, when you ask for subsidies to modernization, you have to improve los ahorros, the savings. You have to improve. You are obliged. If you're not, you have not subsidies. So it's when they are doing this modernization in 60,000 hectares, they have to demonstrate that there is a saving. Si no, you don't have no money.
You said that we scientists don't know, but we have two in the corners and one of Ghana. Your experience is one of the experiences in Spain that is very interesting, because you need to manage two things, technology and governance, but also there is this big discussion on what to do with the savings. And actually, I would like to know, because usually sometimes the savings goes for more irrigation, but in your case, it wasn't the case, right?
When we started the modernization, the first 180 cubic hectometers went to the system just to correct the imbalances that we had. And we noticed that because we have reduced the impact of droughts also. So, and now it's also a question of policy also, and the influence of the ecologists, because they are asking for more water for our Albufera Natural Park, for example, and I'm not sure if it's necessary or not, so amount of water to improve the lake, because it's not only a question of quantity, but quality, because it's a pollution water, and so, but I agree with...
20 years ago, we pacted that savings are going to the system. We're going to the system, to other farmers, to other irrigation lands. Now, the stakeholders, the policy stakeholders, had decided that these savings are going to the river and to the Albufera. We are not so happy because we are in Albacete. One part of these savings were going to Albacete. But now they have decided that these savings are going to the Albufera. We are not so happy because, but it's policy. In the middle, we have the politicians that And that you have mentioned it, the ecologists are very influenceable in our policy stakeholders now. So I don't like the word, but it seems that we are fighting with ecologists with these terms. It's not our intention, but they are sometimes very radical in his positions. So it seems that we are in war, but the first people interested in doing well are the farmers.
This issue about what to do with the water, and it is probably changing because of the prediction of availability due to, in some areas of the world, to reduction of precipitation or increase of ET, and that change in some areas can change the whole system. That also means a reallocation of previous rights, right? That's probably what is behind in Spain too, right?
But in our region, the problem is not the average rain, it's the temperature. Because it's growing, now in Albacete we have 2 degrees more than the medium. That means more evapotranspiration and more days evapotranspirating. So we have less water in the system. But there's no, we cannot say now if it rains more or less, because we have a Mediterranean climate that it's very irregular. So we'll see that in 20 or 30 years with the Basa dates in 30 years. But my impression is the problem is the temperature.
Well, I have heard about something which is happening in Egypt, actually. So they use the water of the Nile mainly to irrigate rice. Rice crop is very important because that's the staple food as well. But as we all know, rice consumes a tremendous amount of water. And if you compare the water use efficiency, the amount of yield per cubic meter of water with other crops like just vegetables, of course, are much more profitable. You can produce much more vegetables than rice with that water. So what I have heard, I've never seen it published, but people were talking about it, that in Egypt, people are saying, oh, let's use the water for the Nile River now to grow preferable vegetables, which on top we can sell to the Middle East, and they give us a lot of dollars for it. And rice, we can buy it very cheap from Cambodia and Thailand, where it is rain-fed. So they are shifting, actually, the use of water from rice to another crop, mainly also for economic reasons, of course. But so there is a shift indeed going on.
I agree with that from my perspective, because rice is, in our area, it's linked with environment necessarily. Also because all the Albufera Natural Park is bordered by rice land. And it's growing or is feeding from the rice land, so that's the end of our lake. So it's not only the agricultural point of view, it's also an environment issue. So.
Where I'm not very, I don't have the perception that we have all the issues regarding waters in dry countries. I'm not the first one in thinking about that. What may happen if we are not able to address this? If we have some examples in areas of the world where we reach the limits if we don't address the issue of more or less not stretching the limits. So what may happen if some of the issues that we know in our areas are not fully addressed? Of water. Yeah, like over extractions or absolutely getting out of wells or, yeah. Just try to be, I mean,
Yes,
you are a pretty good example of places in Spain that are doing pretty well, but it's, we have another picture in the Mediterranean.
In Spain, we have just arrived to this. We have sobreexplotación. Sobreexploitations in many areas. The conflicts now are there with irrigation farmers because the new plants, hydrologic plants, they are forbidden to farmers to irrigate. But it's a question also, one of the problems are the underground, the groundwater, because we have to study more the movements and the possibilities of groundwater. But we have to be a little prudentes, careful, because in some regions of Spain, there are many people pumping water. And when the policy, the government doesn't do anything, there's a problem. We have to, but there's a question also that the users, farmers, have to participate in the governance of water. The example here is that I'm from a region in inland in Albacete, and Ana is in Valencia. And the experience is we have to collaborate to study the problem. Perhaps we don't like the solution of the other, but we have to make a big effort, because if the farmers don't collaborate in the governance, we are lost. It's basically, I think.
We have a lot of possibilities to improve in our area, because we have also used treated wastewater. And also in our area, the groundwater has a lot of possibilities, because we irrigate with superficial water. So we can do change of some rights with other users. We can change our rights, and also we can get deals about give some of our rights depending of the year. And our law do the possibility to do many, many things.
And you were going to say something, T.
Yeah, I just wanted to kind of lift it from local scales to global scales. And are we going to run out of water to feed ourselves? Because we have climate change reducing water availability in most of the agricultural producing areas of the world. We have growing populations who are increasingly eating more rich diets, which are more water intensive. And so on a global scale, we need to feed the future populations, we will need much more water unless we do things differently. And I'm fairly optimistic that we will do things differently, both on the side of production, and all sorts of clever things of like vertical farming and recycling water within closed systems, and also in consumption. I think the example we saw from UK about how much water it takes to provide us with our starchy carbohydrates as our diet has shifted from potatoes to much more rice, massively increased the amount of water. If I can encourage all of my friends to eat more potatoes and eat less rice, we can massively reduce the global water demand. So there are going to be dietary changes which will happen in the future. Some foods will just become very expensive and people will eat less of them. People's diets will change. there's generally a move towards increasing vegetarian or flexitarian diets, which can reduce the amount of water that's required to produce those foods. Now, not in all cases, and I'm a big opponent of people saying we must become vegetarian to save the world's water resources, because it's not quite as simple as that. But in 30 years' time, I think we'll look back on the way we produce food and the food we consume and say, God, didn't we do things in a funny way back in 2022?
Yeah, just maybe to agree with Tim actually, that globally there is of course not a problem at all. If you calculate with the Volkmark index, that's an index who says that a person needs about, I think it's around 4,800 liters per day per person, and that is 70% of the water is for food production, 20% for industry, and 10% in the household. So that's close to 5,000 liters you need. If you count that with a population of 11 billion, you still use only 15% of all the fresh water in the world in 1 year, actually, which comes by rain. But here, of course, the big issue is that it is not fairly distributed, neither in time, neither in place, of course. And I'm sure that, as already mentioned before, there are technical solutions for everything, actually, but the thing is, you need pressure for people to take them. Just to give you an example, Tim was also mentioning in that drip is using more water than the pivots in Senegal, actually. We were recently with Louise, actually, in Tunisia, and there we learned that thanks to solar energy, now farmers has a cheap energy, actually, for pumping water. So instead of using gasoline, now they use solar energy. And they see now that the water consumption for drip increases, actually. So they are misusing it, actually, because for the moment there is not a too big constraint. But if constraints will come, solutions are there. And there is enough water, actually.
The issue really is an energy issue more than a water issue, because also desalination that we're seeing in some parts of the most water scarce world can become a solution for water and make it not a problem at all, as long as the energy source is there to make it cheap enough to happen. So I'd like to ask why I haven't heard anybody say anything about desalination yet.
Well, for desalination, I don't believe to produce water for food production, actually. Because a field, it depends, of course, in which country you are, in which climate you are. If it is, it needs roughly a few million liters of water per hectare during the growing cycle. And if you have to produce that by desalination, that's impossible, even if energy is extremely cheap. So desalination definitely for industry, maybe because they are economic strong, or for domestic use. Definitely, because then we are talking about a few hundred liters of water a day.
But think about an even bigger picture. Desalination can dictate what the actual value of water is, because it's creating new water. So the cost of desalination and delivering that water to agriculture can become the value of water that then dictates the economics around decision-making for what you're growing and how you're growing. We see it happening already in Israel, that we don't desalinate for agriculture, but half of our water going to municipalities have become desalinated water, so it's very important to the water economy and therefore to the entire economy, and it's dictated the price, the actual value of water. And then it changes how farmers make decisions, because the water becomes more valuable than it used to be. But if we're not going to have water, then that value is going to go up, right? When you have no water, the value is infinite. So again, I do think we can scale up. Israel's very small, so our large scale is still a small amount relatively of desalination. But I could imagine that. I think we're starting to see it happening in the south of Spain and in the east of Italy and in some of Australia as well. The most water scarce places that have economies that can think about changing things to make things expensive, right?
No, the desalinization in Murcia in the south is beginning to function. The problem was the cost. But now with photovoltaic energy, they are arriving to make a low cost. The next problem is that you have to mix this water with the natural water, because we have problem with some salts and boro, and there's, you have to mix the water. But for Murcia now is the solution. They have cut the trasvase Tajo Segura, is water bring it from in Spain, from 500 kilometers from la Sierra de Cuenca, and they have limited this amount of water to 300 hectometers, but they are supplying with desalinate water in the amount of water. We are doing it. The problem is the cost, energy cost, but they are arriving now to lower the cost, and is profitable now.
Yeah, I think also that desalinization as such, maybe not for agriculture, I don't believe so much in it, but well, as he mentioned, the mixing, of course, of slight saline water with fresh water, and then there will be another shift, is to other types of crops which can support better the salt, like for example barley or something like that, to grow that. But still, there is the problem of, on the long term, that you get anyway, salinity problems on the long term become stronger and stronger, unless there is some flushing. So it means you will need more water actually to clean it, or you need winter rains which can leach it out of the soil.
It also is a problem of infrastructures, but because sometimes the stations are far away from the irrigable area, so you have to invest also in infrastructures, and the farmers cannot allow the cost. So.
No, I think that in general the question is, okay, it's necessary to apply science, technology, it's necessary to apply desalinization, all of the things, and sometimes in the table say it's not necessary maybe, because for instance the farmer wants to produce maximum, so it's not very interested in regular deficit irrigation. And it's true, of course, but the problem is in some areas. Not everywhere has enough water. So in some specific areas, Israel, Murcia, in this place, nobody likes to use wastewater, treated. Everybody prefers to use a wonderful water for irrigation. The problem is that there is not water for that. So or you apply technology, or you apply desalinization, or you use wastewater, or you don't produce. Okay, you can say, well, don't produce. You can modify your economy, yes, but this is difficult sometimes because, for instance, in Murcia, well, I don't know, but the importance of the production, agricultural production, crop production is very high, and you must try to maintain this. So I think that these technologies, maybe I don't know if at world scale is something that you can promote, but in some areas it's clear that it's necessary to apply, because in other way you must finish with the system of crop that you have. Well, in Murcia it's true. Now they are trying to use the desalination. Well, you explained very well. The problem is that it's expensive. I think that is not a problem. I think that sometimes the farmers also look for some I don't know, problems that there are. No, this water is not very good because it has a lot of water. No, I think that the problem is that it's very expensive, of course, obtain, no? And they prefer to use the water for the river or for the transfer or something like that. But I think that this is a solution if, obviously, we can reduce the crop production. And against what's more important, governance or technology, I think that is very difficult. So the governance is very, very important to apply the technology. If you have a very good technology and there is not a good system of governance to apply, some push for the politician or something like that to apply, maybe it's not doing. But of course, only with the governance of the water, in some specific cases, when you have no water, you need technology. So it's not very. It depends on the area. Maybe sometimes it's better the technology. Well, I am working in technology, so I prefer technology than governance. But it's not good excellent.
One thing important: the price of the water.
Yeah.
He has said that with the desalination water was very expensive. The problem in Murcia that the water was coming from the inland of Spain was very cheap. See.
You are from inland Spain.
Yes. No. And when you put a low price to water, you are pushing the people to use water with no limits. So you have to reach society, politicians, the stakeholders in our communities. We have to put a real price to water. Because if you don't put this price, people is going to bad use water or to spray water, not to use good the water. One of the problems was in Spain, the trasvase Tajo Segura, the price was 25 centimes euro meter cubic, I think. Okay, desalination water is €1 meter cubic. So the farmer was used to a low water price. When you have told him you have to pay this, I don't want. But they make farming that allows to pay this cost. They will win less, but they are profitable. In this special farming, vegetables for Europe and not in citrus, not in almonds, but in lettuce, vegetables, cucumbers.
Yeah, I think that this is a local situation. I don't know if it's extrapolable to more areas in the world. I suppose yes, but many, yeah. But of course, the price of the water is very important. Yeah, very important. And there are some crops that maybe you can pay more for the water than other. No, I agree with you in the most of the things, but not that the water of the transfer is very, very cheap. It's more cheap. It's cheaper than the desalination because, of course, 30% part, but 30 cents of cubic meter is you know the price in Andalusia, and it's cheaper. I don't know if you paid 30 cents. I don't know how much. Yeah, depends on the community. No, but it's not, yeah, okay, but. Yeah, no, anyway, yes, the price is very important. Maybe the governance, the governance is very important to fix this kind of price and to help maybe the farmers if they cannot obtain this money or to change the crops to make crops more profitable. You are right, it's true. But the Murcia, I think that is, I don't know if, well, in Israel maybe you have similar problems.
That's something we try to transmit this morning, but it's to the table to discuss. We are reaching almost the 1 hour and 30 limit, and I think it's a good time for the four of you in the table if you want to say some final comment or final remarks or some idea that was missing and you want to leave on the table before we adjourn. So we can start now from you, Anna, so we change sides.
I think it has been a very interesting journey. The resume is both things, technology and governance, at least in my area, are important to get improving. And I don't have to say most things. You talk about fertilizers, and of course in drip irrigation, it's helping us to reduce the consume of water also, because they are very expensive now. And the old farmers are asking for less water only to save money. So it depends on the area. We have a lot of tools. We have many things to do to improve. And we will need the support of all of you. And thank you.
I think most of things were said. Just a small thing about the fertilizers, which is of course another constraint. If there is next to the water. And then maybe an interesting, I don't know so much about deficit irrigation actually. So if you apply deficit irrigation, you put your crop under some stress and he is going to transpire less and is going to make less biomass actually, but of course more yield, that's what we need. So you need also less fertilizers actually. So deficit irrigation is not only saving water, but also saving fertilizers because you need less canopy to develop.
Okay, thanks. I think a really important take-home message is that we have lots and lots of tools, whether they're technology tools or governance tools. But before we can use those tools, we really need to know what's the problem we're trying to solve. And water scarcity, water issues is at the center of a number of complex systems. Social system, a food system, an energy system, an environmental system, and they're all interacting with each other. And you sort of push here and something pops out there, and you push here and it pops out there. We talk about raising the price of water. Well, that means the price of food's going to go up. And we all know at the moment what's happening to the price of food. And that means that people who are less able to afford food go hungry. So moving a lever to increase efficient use of water here is creating poverty and hunger over here. The difficulty is trying to understand how all of these systems interrelate, and they all interrelate differently at different scales, whether it's in a local community scale or a global scale. If we had very cheap energy, and we could desalinate water and we could pump it for nothing, then we'd all be out of a job. I mean, we're almost out of a job already. But I think everybody in the room will still be in a job for a long time. Yeah.
For me, the experience is you must, you have to have more farmers in these researching projects, because everything I come to these projects, I'm the only farmer. You are talking about farming, you are studying farming, but there's no farmers. And that doesn't mean I'm right and I have to tell you how to investigate, to research, but sometimes the problem is that we are not participating in these projects. The problem is there's mainly there are no farmers, young farmers. The average age of farmers now is very high. I don't know if we are talking to no farmers in 20 years because behind me there's no one. In 10 years I've been jubilado or jubilated, and and for me it's one of the main problems. We are talking about farming, but if there are not farmers, no food.
Okay, thanks so much. I think you summarized pretty well. All of you, 2 or 3 things. I mean, Rosanna raised it, but it's 2 or 3 things that makes myself uncomfortable when you see that there are some. I mean, you said we need to ask the right question, and sometimes we need to ask the right question with the right people. And I always wonder what we are doing sometimes in the academic world. And the people that knows me, I know this is not to make you happy, Miguel. So I think that it has been to me a fantastic morning. And I hope that I want to thank on behalf of the whole project to the 4 of you. And I think we can adjourn the round table and the day. So thanks so much.